In the quest for a sustainable future, humanity stands at a crossroads. Fossil fuels, the backbone of industrial civilization, are driving climate change at an unprecedented pace. Renewable sources like solar and wind offer hope but struggle to meet the relentless global demand for energy. Amid this energy conundrum, one technology looms large, often misunderstood, yet brimming with potential: nuclear power. Once feared for its association with catastrophic failures and Cold War weaponry, nuclear energy is experiencing a renaissance as scientists, policymakers, and innovators revisit its promise as a clean, reliable, and virtually limitless energy source. This video delves into the science behind nuclear reactors, their evolution, their role in combating climate change, and the challenges and opportunities that lie ahead. How nuclear reactors work. At its heart, nuclear energy harnesses the power locked within the atom. Unlike fossil fuels, which release energy through chemical combustion, nuclear reactors tap into nuclear fission, the splitting of atomic nuclei. The most commonly used fuel is uranium-235, a naturally occurring isotope that, when struck by a neutron, becomes unstable and splits into smaller fragments. This process releases an enormous amount of energy, primarily in the form of heat, along with additional neutrons that sustain a chain reaction. In a nuclear reactor, this reaction is carefully controlled. The heat generated warms water into steam, which drives turbines connected to generators, producing electricity. This elegant process is remarkably efficient. A single gram of uranium-235 releases energy equivalent to burning nearly 3 tons of coal. Moreover, it emits no carbon dioxide during operation, making it a cornerstone of clean energy discussions. The reactor core, where fission occurs, is a marvel of engineering. Fuel rods containing uranium pellets are surrounded by a moderator, often water or graphite, that slows neutrons to optimize the chain reaction. Control rods, made of materials like boron or cadmium, absorb neutrons and regulate the reaction's pace, ensuring safety and stability. A coolant, typically water, circulates to transfer heat and prevent overheating. Encased in thick concrete and steel, modern reactors are designed with multiple redundant safety systems, a far cry from the rudimentary designs of the mid-20th century. Nuclear energy's origins are tied to the dawn of the atomic age. In 1938, German physicists Otto Hahn and Fritz Strassmann discovered fission, inadvertently setting the stage for both the atomic bomb and peaceful energy applications. During World War II, the Manhattan Project weaponized this discovery, culminating in the bombings of Hiroshima and Nagasaki. Yet, even as the war ended, scientists like Enrico Fermi saw a different path. In 1942, Fermi achieved the first controlled nuclear chain reaction at the University of Chicago, proving that fission could be tamed. The first nuclear power plant to generate electricity for civilian use came online in 1954 in Obninsk, Soviet Union, producing a modest 5 megawatts. The United States followed with Shippingport in 1957. By the 1970s, nuclear power was heralded as the future, with reactors sprouting across North America, Europe, and Asia. At its peak, nuclear energy supplied over 17% of global electricity, a figure that has since declined but remains significant. This golden era was punctuated by setbacks. The 1979 Three Mile Island accident in the U.S., the 1986 Chernobyl disaster in Ukraine, and the 2011 Fukushima meltdown in Japan fueled public distrust. Each incident exposed vulnerabilities, human error, inadequate safety protocols, and natural disasters, prompting a reevaluation of nuclear technology. Yet these tragedies also spurred innovation, leading to safer, more resilient designs that define today's reactors. As of March 15, 2025, the urgency of climate change has never been clearer. Global temperatures have risen 1.2 degrees Celsius above pre-industrial levels. Extreme weather events are intensifying, and the window to limit warming to 1.5 degrees Celsius is narrowing. The Intergovernmental Panel on Climate Change, IPCC, warns that achieving net zero emissions by 2050 requires a dramatic shift away from fossil fuels, which still account for over 60% of global electricity generation.